type of chi-squared test, and this one is called the goodness of fit test. So just to remember what we're dealing with in terms of distribution, we are still dealing with the chi-squared distribution. So we're still going to be interested in two important key characteristics of the curve, which are determined by the degree of freedom. We're going to be looking at the critical value and then the significance level, and we're going to compare that to the chi-square calculated and the p-value. So same as the independence test. Okay, so what's different from the independence test is that now the calculator is not going to calculate the degrees of freedom for us. We need to be able to calculate the degrees of freedom. When we're dealing with the goodness of fit, we're going to have observed data and expected data. So it's a little bit different how we organize our data than the independence test. So bear with me with my explanation of the degrees of freedom. Suppose that you want to wear a different hat every day of the week. So you have these beautiful 7 hats. Well, on the first day, you're going to have a choice of 7 different hats that you could wear. So for example, you choose the Santa hat. Well, that one's gone. On the second day, you have 6 choices of hats. And this continues so on and so forth. You have the third day, you have 5 choices. The fourth day, you have 4 choices. Eventually, on the 6th day, you're going to have only 2 hats remaining. So you're going to have still a choice between 2 hats. But on the 7th day, you're going to be stuck with whatever hat is remaining. So if we kind of recap what just happened, in your entire week, the 7 days, you could only choose 6 days. So you only had a choice 6 of those 7 days. Well, when we're dealing with degrees of freedom, there's a definition that says the degrees of freedom are often broadly defined as the number of observations in the data that are free to vary when estimating statistical parameters. So all in all, degrees of freedom are just the number of options we have, or the number of pieces of information, minus 1. So we had 7 hats, and 7 minus 1 is 6. So we had 6 days we could choose something. So all this beautiful explanation to say that the degrees of freedom are simply the number of choices we have, minus 1. Okay, now that we have that settled, let's talk about the null hypothesis and the alternative hypothesis when we're dealing with goodness of fit. At this point, it would be good to mention that the goodness of fit test is used when we want to check if our sample matches a certain distribution. So we want to make sure it matches or it follows a given distribution. So the null hypothesis is always going to be that the observed numbers are as expected. So depending on this situation, this is going to vary because the expectations can vary. So here's an example. If we roll a die 60 times, well, we're expecting the die to be fair. So we're expecting to have the 1 fall 1/6 of the time, the 2 1/6, and so on and so forth. So the alternative hypothesis to that would be that the dice is not fair. So that would be the alternative. Another example we can use goodness of fit is if we're looking at scores on an IQ test. Well, an IQ test, we can imagine that it's normally distributed. So we would expect the scores to follow a normal distribution with a mean of 100 and standard deviation of 10. And then the alternative would that it just doesn't follow that distribution. And another example is if we have students in 8th grades and we ask them when is their birthday in a week, so does it fall on a Monday, on a Tuesday, or whatnot. Well, we would expect to have a pretty uniform distribution. What's a uniform distribution? Well, that just means that it's an equal chance of happening. So the dice actually represented a uniform distribution, equal chance of happening for all of the outcomes. So this is a little bit different from the independence test, because notice that the null hypothesis is not always something is independent. It's going to be very dependent of the situation we're in. But all in all, our observed data is going to follow whatever is expected. And of course, the conclusions do not change. It is exactly the same for independence and goodness of fit. We're going to be accepting the null hypothesis if we are dealing with a chi-square calculator which is smaller than the critical, or if we are dealing with a p-value that's bigger than the significance level. And we're going to be rejecting the null hypothesis, therefore accepting the alternative hypothesis if our critical is smaller than the calculated, and if our p-value is smaller than our alpha significance level. So same conclusions here. Let's do an example to understand what's happening. A company claims that in a certain bag of candies, they produce 25% red, 40% green, and 35% yellow. You try to check this claim and buy a bag of candies. You find that there's 63 red, 72 green, and 65 yellow candies in your bag. Is your sample consistent with the distribution the company claims? Use a 0.05 level of significance. Okay, so this question is asking us to claim if the distribution is correct. So the first thing we need to identify is our null and alternative hypothesis. We want for the null hypothesis the company to follow the claim. So that means that there's 25% red, there's 40% green, and 35% yellow. Our null is that it does follow this distribution. And the alternative is that it does not follow this distribution. So what we're going to do now is we are going to calculate the chi-square goodness of fit. Now, very important for the goodness of fit, we are going to have to input ourselves what the degree of freedom is. So the degree of freedom for this situation, we think, how many candies do we have? We have red, green, and yellow. 3 different candies. Therefore, our degree of freedom for this stats test is going to be 2. 3 minus 2. Okay, let's go and talk about how to calculate all of this. In your calculator, you are going to insert a spreadsheet when we are dealing with goodness of fit. In the spreadsheet, the first column is going to be the observed data, and the second column is going to be the expected data. Now, how do we calculate this? Well, we have to think about what is given to us. We have our specific bag of candy that we chose has 63, 72, and 65 candies. When you add that together, this is a total of 200 candies. So out of 200 candies, these are the numbers that represent the observed data. So my observed data is going to be the 63, 72, and 65. Now we need to calculate the expected data. In order to calculate the expected data, well, we need 25% to be red. So 25% of the total 200 that we had in our bag, that means we are expecting 50 to be red, 40% we are expecting to be green, and then 35% we are expecting to be yellow. So what we're doing in our calculator is we're putting in the observed and the expected data. So making sure that the expected data, we know how to calculate that given the percentages and the total amount of candy in our given bag. Okay, now once we have this, we need to tell our calculator to run a goodness of fit test. So we're going to go into menu, statistics, stats calculation, and you're going to find the chi-squared GOF, goodness of fit. Our observed data, we labeled observed. Our expected data, we labeled expected. And notice that they ask us to input the degrees of freedom here. So we have to input it ourselves. So the degrees of freedom we said was 2. And then this is just where the information is going. And then you don't need to have anything shaded. So you click OK. And now we have the information given to us in terms of our chi-square calculated value and our p-value here. Okay, so now that we have our two values, we can do a conclusion. In our question, we had 0.05 level of significance. So this is our level of significance, which we compare to the p-value. Our p-value is 0.103, which is bigger than our significance level. So since it's bigger than our significance level, we are in this sector here. Therefore, we are going to be accepting our null hypothesis. So we are accepting that the distribution of candies does follow the given claim, which is 25% red, 40% green, and 35% yellow. Okay, so that was for our first example. Let's do our second example. I'm going to do another example, so I'm going to insert a new problem, and I'm going to go into a spreadsheet. Okay, second problem. The table alongside shows the grades received by university students taking a second-year computer science course. In the following semester, a new coordinator is appointed for the course. The new coordinator is concerned by the high number of high distinctions and distinction awarded, and he wants to determine if the course could be adjusted. It is considered that usually 5% of students receive high distinction, 10% distinction, 15 credit, 40 pass, and 30 fail. Conduct a chi-square goodness of fit to determine whether the course should be adjusted with a 5% level of significance. Okay, for this question, we are given the expected distribution in percentages, and we are again given the observed data with a total of 150. So we're going to start by doing our alternative and our null hypotheses. The null hypothesis is that we follow the given distribution, 5, 10, 15, 40, and 30%. So that is going to be our null hypothesis, that it follows the given distribution. The alternative is that it doesn't follow the given distribution. So notice here that they're very specific in their null and their alternative hypotheses. Now that we have that, let's talk about the degree of freedom. So the degree of freedom, we have 1, 2, 3, 4, 5 different courses or different grades. So therefore, the degree of freedom will be 4. 5 minus 1 is 4. Okay, let's put everything in our spreadsheet. We're going to have our observed data, and we're going to have our expected data. The observed, we have 16, 21, 21, 59, and 34. Now for the expected, make sure that you're doing your calculations correctly. Our total is 150, so 5% of 151. You can simply put that into your calculator as a calculation. Then we have 10%, 151. And then the next one is 15%. The next one is 40%. And then the next one is 30%. Good. Once everything is inputted, then we're going to go into menu, statistics, stats, test, and we're doing a goodness of fit. Our observed, our expected, and we said our degree of freedom was 4. Okay. And now we have the important information here. Chi-squared calculated and our p-value. Again, since we are only given the level of significance here, we're going to compare that to our p-value, so we're not using the chi-squared calculated in this situation. So, with our technology, we get a p-value. This p-value is smaller than our significance level, so therefore we are in the region where we are going to be rejecting the null and accepting the alternative. So we are going to be saying that we are accepting the null hypothesis so that at least one of these percentages is incorrect. And that's going to be for our second example. Now, the two examples we've done so far, we were good and we didn't have to change anything. That is because the expected values were higher than 5 for all of our situations. So the only exception that we have when we're dealing with chi-squared tests, both independence and goodness of fit, is that all of our expected values need to be higher than 5. If they are not higher than 5, then we need to combine some categories together and then run the test. So for example here, if this is our expected frequency, well, we see that there's 3 categories here that are under 5. So we would combine these 3 together, so 30 to 40, 40 to 50, and 50 up. We would combine this and we would have a new data where you're using only the 14.9, 14.1, 15.6, and the 5.5. So these are the 4 values that you would use as your expected. And if you had to combine your expected, well, you also need to combine your observed data together. So you would only have 4 numbers for observed and 4 numbers for expected. So this is an important limitation that we need to be aware of. Okay, example 3. It is believed that the weight of a packet of flour can be modeled by a normal distribution with a mean of 7.9, 7.8, and a standard deviation of 1.2. For a sample of 1,000 packets, calculate the number of packets that would be expected under 6 kilograms. Okay, so for this one, we have to think that we are dealing with a normal distribution where we are having a mean of 7.8 and a standard deviation of 1.2. So this is a distribution we are dealing with. Well, knowing this, we can find out what is the probability of having x be, for x to be smaller than 6. So how we do that, we go into our calculator and we do the normal distribution calculation, so normal CDF. We get the probability of x being smaller than 6 is 0.0668. And since we have 10,000 packets, well, how many do we expect to be under 6? Well, that's just going to be our probability times 1,000. So we are going to be expecting to have 67 if we round to 67 if we round to the whole digit. And there would be the same calculations. So what is the probability that x is going to be bigger than 8? And then what is the probability for c that x is going to be between 6 and 8? So when we do all these calculations, we are going to get our probabilities. So we get 0.434, 0.499. So if we round it to the nearest whole number, we are expecting to have 434 that are over 8 and 499 that are between 6 and 8. So that's how we do the first question here. Next, a sample of 1,000 bags are taken and the frequencies of the weights are shown below. So the weight of it being, so now there's 1,000 bags that are taken and these are the observed data. A significance test at 5% low significance is conducted to see if there is evidence to suggest that the believed mean and standard deviation is incorrect. State the test that we would use. Well, we're going to want to show that a certain sample matches a normal distribution with a mean of 7.8 and standard deviation of 1.2. So since we're trying to show that it's going to match something, so it's going to follow distribution, we're going to be using a chi-squared goodness of fit test. And we're going to write down our alternative and our null hypotheses. So the null hypothesis is always that it follows a certain distribution. So we're going to say the proposed distribution. And what's the proposed distribution? Well, this is that we have following a normal distribution with a mean of 7.8 and a standard deviation of 1.2. We're going to say that this is correct. And then for our alternative, well, we're going to have the proposed distribution. Distribution is incorrect. So just the opposite. Okay, so that is for our null and our alternative hypotheses. Write down the degree of freedom of this distribution. Well, the degrees of freedom, we need to calculate that ourselves. We are dealing with a situation that there's 3 categories of separating these packets of flowers. So 3 categories, 3 minus 1, we have a degree of freedom of 2. Now find the p-value. Well, now we need to go into our calculator and we need to run a chi-square goodness of fit test. So in your calculator, you're going to have your observed data and you're going to have your expected data. So the observed data is going to be our 81, 514, 405. And the expected is going to be our 67, 434, and 499. So this should be going in your GDC, and you're going to be putting in all of this information. And your GDC is going to be able to give you, so please pause this video at this point, try it out, and then you should be getting a p-value of 0.07. Okay, so since we have a p-value of 0.07 and we were doing a 5% level of significance, well, we're realizing that our p-value is bigger than our level of significance. So since it's bigger, we are going to be accepting the null hypothesis. So we're going to be accepting the null hypothesis here. Okay, so in this situation with a 5% level of significance, we would accept that it follows the distribution. The last part of this question is G. State with reason whether the conclusion would have been different with a 10% level of significance. Well, in this fact, yes, it would have been different because now it would have been, our p-value would have been less than the significance level. So therefore, we would have accepted the alternative hypothesis. So very different outcome for a different level of significance here.